So we're going to start off with an example for the work section. And in this example, what we're going to have is carbon dioxide gas. It's going to be in a piston cylinder assembly, and it's going to undergo a process from a state where the initial pressure is 5 psi, volume is going to be 2.5 cubic feet, and it's going to go to a state where pressure is going to be 20, volume is going to be 0.5, and the relationship between the pressure and volume is given by this expression right here. Okay? And the volume in this expression is given in cubic feet, and pressure is in psi. We want to determine the work for the process in British thermal units. Okay? So that's our problem. Now, let's look at what's given here. All right, so let's write it down. So first we've got our initial pressure. So P1, that was 5 pound-force per square inch. The volume that went along with that is 2.5 cubic feet. Then we have our conditions at state 2. So the pressure here is 20 psi, and volume is going to be 0.5 cubic feet. Okay? So this is what we've got, and then we've also got this relationship here, all right, between pressure and volume. So we want to make sure we make note of that. All right, so there is the expression. Now, what we want to do is we want to find the work in the process. Now, before we start looking at equations and everything, let's draw a picture so we can kind of see what's going on. So this is a piston cylinder assembly, so I'm just going to draw it like this. There's the piston, and here I've got the CO2. Initially, my pressure is going to be at 5 psi, and this volume in here is 2.5. Now, this is what we start out with. Now let's look and see what happens. So our pressure is going to increase, and the volume decreases. Okay, so basically what's going to happen is we're going to be pushing this piston to the left, right, because we're reducing the volume. So at the second state, if we draw our cylinder again, now the piston is going to be further over to the left. Okay, so we still got CO2 in here, but now the pressure is 20 and this volume is a lot smaller. Okay, so we move the piston to the left. So since we had a volume change, we know work was done. Now we need to find the work. Okay, so it's always going to be helpful to draw these pictures just so you can visualize what's going on. So remember, if we reduce the volume, we're not changing the amount of matter we have, so that's going to increase our pressure, which you see that's what happened here. Pressure went up as volume went down. Okay, so let's write out our equation for work. So if you remember, work is going to be the integral of pressure times the change in volume, and our limits will be volume 1 and volume 2. Now we were given this expression for pressure. Notice it is a function of volume, so that'll be useful. So essentially we need to take this expression, plug it in for P. Okay, so we're going to do the integral of 23.75 minus 7.5 times the volume, dV, and then think about your limits. We need the initial volume, so what was that? That was 2.5. So we got 2.5 there, and then our final volume, V2, is the reduced 0.5. Okay? So now that we have this, we just need to integrate. This is a simple integral to do. So you just integrate, and you're going to get 23.75 times the volume minus 7.5 times V squared over 2, and then we evaluate at our two volume numbers. Okay. Now, we've got this. Now let's look and see about our units. Okay, I haven't written any units down so far, but notice up here in the problem statement, volume is given in cubic feet, pressure is given in pound-force per square inch. So we can't be combining inches and feet here. So we're going to have to do a conversion. So let's write need to convert units. All right, so pressure is in pound force per square inch. We need to get this to pound force per square foot. Okay. Now the way we're going to do that is let's take this function that we have, and you could do your conversion before you integrate also, it's up to you. I just happen to do it afterwards. So there's what we get after we integrate, and we're going to take that and we're going to multiply that by 144 inches squared per foot squared. And then we're going to evaluate this whole thing at our values of volume. Okay. So now we've got that. And remember, this expression here is pound force per square inch. So the square inch part cancels out with this one. Okay. And then it's just going to leave us with pound force per square foot. Right? And then these volume numbers, these are cubic feet. Okay. So the units will all work out. All right, so now we just need to plug everything in. So if you plug in 0.5 into that expression, you get 1,575. Units will be pound force times foot. And then when you plug in 2.5, you'll get the negative 5175 foot pound force. Okay. When you subtract these two, you get negative 3,600 foot pound force. And now we don't want this unit, right? We want British thermal units. We want BTU. We need to convert to that. See, I told you guys we'd be doing a lot of conversions in here. So let's take the negative 3,600 and we're going to convert over to BTU. So if you look in your conversion table, you'll see that 1 BTU is equivalent to 778.17 foot-pound force. Okay, now look and see, make sure your units work out. So those look fine because we're left with BTU. So now, once you divide these two, you'll get a negative 4.626 BTU. This is our work that has been done. Okay. Now let's think about that result. We got this negative sign, right? Now remember we had the sign convention and I said the sign convention would be important. Well, this is an example why. So this sign here is telling you something. This is less than 0. So this is telling you that work is being done on the system. Now let's think about what that means. If we look up at our picture that we drew, we already know from looking at this, since the volume is being reduced, we know something is pushing the piston to the left. Right? So something is causing that piston to move. Now this system itself is not generating any sort of energy that would make this piston move to the left. Okay, so it has to have some sort of external energy source that's causing that motion. So work done on the system means there's something external to the system that is transferring energy in, right? So something is causing motion from the outside. So that's why those signs are important. So here, energy is transferred into the system. Okay, and that's why that piston is able to move to the left. Without that external energy, it wouldn't be able to move to the left. Okay, and one more thing I want to show you guys. Let's look at this graph. Sometimes it'll ask you to draw something on PV coordinates. So that's just wanting basically a 2D drawing where we have pressure in the vertical axis, volumes on the horizontal axis, and you're just going to label your states. All right, so initially we had a volume of 2.5 and we had a pressure of 5, And then at the second state, we had 0.5 for volume, and then our pressure went up to 20. Okay, so now if you were to draw a line connecting those two, it's going to look like that. Okay, and these are supposed to line up here. Now you've got this curve here. So basically this was our curve relating pressure to volume. So we know it looks like that. Now you've got this area under the curve. So essentially what we did is we integrated this curve, and the area under it is going to be work. Right? So remember, when you integrate, you get the area under a curve. So here you go. So our work is the shaded area. Right? So calculus there. So this curve right here is 23.75 minus 7.5 V. Okay? And you usually want to put your units on here. So you can put like that. Okay, so if it asks you to draw something on PV coordinates, that's what it's talking about. All right? And just keep in mind, when you have this line here connecting your states, that when you integrate that line, you get the work done, because you're finding the area under that curve. All right, pretty cool stuff, guys. Okay, that's the end of that one. I will see y'all in the next video.